So we saw this one grand unification effort where AdaGrad and RMSProp are basically just adaptive algorithms. Both AdaGrad and RMSProp have a very slightly simple version in terms of momentum. In fact, there's no momentum at all here. AdaGrad just keeps adding the B. B is where we were capturing the curvature directly, right? To a G which is accumulated over time, GT minus 1, as you can see here. And then RMSProp tries to fix an issue with AdaGrad. There's a diminishing learning rate in the case of AdaGrad, alpha T, HT inverse start going to 0. So it says, let's take a convex combination of GT minus 1 and DT. Okay, because here, if you see this, if you keep adding, then what happens? GT minus 1 plus DT. The next epoch, what would you have? What will keep accumulating in AdaGrad? HT is GT minus 1 plus DT. Huh? DT? How is DT accumulating through GT minus 1 or GT? Yeah, so this is GT. So GT is updated as GT minus 1 plus DT. That component starts becoming very big, right? The GT component becomes very big and dominating. Sorry, DT becomes very dominating because you're adding it at every epoch. Okay, so therefore, there's a kind of convex combination so that you ward off that diminishing learning rate created by AdaGrad. And then Adam just says, well, we'll put together RMSProp with momentum. So ADAM basically is adaptive momentum. That's how it expands. Now, without getting into the details of how the alphas and betas, etc., come out to be, let's quickly get a feel for a very nice rudder.io. I think it's still relevant. So there's an overview of gradient descent optimization algorithms where we can go through all the gradient descent variants and momentum, Nestor accelerated gradient, AdaGrad, AdaDelta, RMSProp, right? And their batch versions, batch and stochastic versions, stochastic batch versions. So this is just a Nestor which you're already aware of, presented again, AdaDelta, right? Now let's understand a little bit of what this this ADAM itself is. In fact, I left that as a homework problem. So what is ADAM itself? ADAM is basically heavy ball momentum plus adaptive, as you could probably figure out here. So in the case of ADAM, right, the gamma is 0. Gamma is 0 would mean that there is the gradient computation, which only depends on the current WT and not the velocity component. So that is exactly heavy ball, right? So gamma T is 0. In fact, except for the Nestor accelerated gradient NAG, all the others have gamma set to 0. So obviously you may wonder, what about a variant of ADAM which uses the Nestor accelerated gradient? That's another variant possible. In fact, the blog also lists that. What else is interesting here? The way ADAM is implemented is interesting here. Okay, so I gave a hint about it when we talked about Nestor accelerated gradient. I said, well, we could actually have two different parameters. You remember X and Y? We were accumulating X and Y separately. Something similar is happening here. Okay, so what you're accumulating are the gradients and the second order, the squares. So you're accumulating gradient and the squares gradients, both the mean statistic and the kind of variance, second order statistic, first and second order. So yeah, the green part is basically the first moment and the pink is the second moment. The other important part about ADAM is these two, MT and VT, are initialized to 0. So what you do is to avoid their biasing towards 0, especially when decay rates are small, you normalize them by 1 minus beta t. So I had said that there's a reason why there's this 1 minus beta t is coming up here in the denominator, highlighted in yellow. And that reason is that reason is exactly this, to counter the biasing of the MT and VT, which are already initialized with 0. The decay rates can become small because of that, and therefore there's a normalization. Okay. So yeah, this is normalization, and the rest is very simple. It's basically this update is exactly otherwise the heavy ball momentum update. Okay. Yeah, so I just made another comment that this normalization, basically division by 1 minus beta t, will make this entire thing greater than 0. So you kind of bump up the decay rate. Okay, so this again going back to this slide, you see 1 minus beta t is there in alpha t, in beta t, and this is basically the decay rate, and you're trying to bump up the decay rate and not make it go too small. Okay. There have been numerous extensions of the above techniques. It's there in the AdaDelta optimizing gradient descent blog. And there is also this NADAM. What would you expect NADAM to be? Nestor, right? That's what I said. So that variant is also there. NADAM is Nestor accelerated gradient plus adaptive. There are others like AdaDelta you'll find in the blog, which is an extension of RMSProp, which uses the root mean square operator. Okay, and then there was also a kind of error, a theoretical error in ADAM, and it was not converging even for convex functions. So AMSGrad, okay. AMSGrad, what it does, it's basically ensures that the VTs, the accumulated, right? VT was accumulated squares of gradients. Now, obviously, you would expect it to be positive, right? VT should be accumulation of squares should be positive, but thanks to some of these steps and some of these steps, it was actually turning out to be negative, the numerical errors. So therefore, a simple fix to that actually made the convergence possible. Actually, this is more to do with the theoretical analysis. So practically, obviously, it's sum of squares, so you will not have a problem. But theoretically, with the additional assumption that VT is greater than 0, they were able to fix the convergence. Okay. So I'm going to run through these because I want to move on to the next topic. The first theoretical result was shown for AdaGrad. That's where things began. Adaptive gradient. And that's the reason we spent a little bit more time on quasi-Newton methods, because that gives you a very strong tool to prove convergence through something called regret bound. And in fact, that's characteristic of all these online algorithms. So far, we have not used regret bound to show convergence. What do you understand by regret? And how do you think it's related to stochastic? Yeah. But what is regret? A desirable, so a gap between the desirable outcome and what I have, right? I have a stochastic sample of the data, whereas if I had the access to the entire data set, my result could have been different. The gap between the two is a regret. And it is very characteristic of the stochastic family of algorithms. Okay. So yeah, there was also a bug. ADAM had a bug in its analysis, and it in fact carried forward to the others. And so they didn't have theoretical regret bounds backing RMSProp, AdaDelta, and NADAM, but then ADAM had that. So AMSGrad basically showed regret bounds to the modified version of ADAM. Obviously, all these convergence analysis, even with regret bounds, are only for convex functions. Okay, but nevertheless, convexity remains of great interest because that's the only window into the space of convergence. I mean, the primary window. Other important point to mention here, which also gets highlighted in our struggle, right? We struggled with different RMO conditions. We tried one version, it didn't work. We go through the collab notebooks. So the reason AdaGrad has become very popular is because this adaptive gradient gives you a nice way, curvature influenced way of handling the step size, which all these other RMO conditions, etc., were struggling with. So let's look at some of the key takeaways from some of the recent papers. So this is the original ADAM paper, ICLR 2015, and you can see the kind of characteristic differences. Stochastic gradient distant with Nesterov, that is the one in red. What do you observe? So stochastic gradient descent with Nesterov doesn't involve any adaptive step, but it is just momentum. And what we find is you need some gradient accumulation over time for momentum to be effective. Okay, so it actually, you see, it steps out, it starts out to be slightly bad. Right? It starts out, it takes some time for it to emerge as a winner, the red part, right? Adaptive, what is the advantage of adaptive? The green curve. I mean, it quickly jumps down, right? But then what happens? Then slows down. Okay, so this whether we appreciate other plots or not, this plot is important. Let me highlight it again. So the adaptive guy, it dips quickly, but then becomes sluggish. On the other hand, the ADAM guy, it takes some time and then crosses over. There's a momentum. Sorry, there's a mistake in the type. What we show is ADAM has both, best of both worlds. So there's momentum. So ADAM, which is adaptive plus momentum, does better than both. Right? So it starts off roughly here, but then, yeah, and not really emulating, but you can see that it overtakes both of them fairly quickly. This is ADAM. Okay, just registering this image is also good. So this also tells you that, adaptive was very handy for showing convergence through regret bounds, but practically it's not good enough. That's where we need momentum based methods. So this is also making a case for combining theory and practice. Okay, so summarily, the adaptive gradient can significantly improve upon stochastic gradient descent in sparse feature sets. This is adaptive, AdaGrad. I mean, it gives you a lot more leeway into how you set the learning rate, etc. But also, it turns out that in dense settings, in deep models, it can, it also has fair bit of its problems. So ADAM, etc., try to fix this issue. And generally, momentum all improves upon the non-momentum variants that you saw here again, right? I mean, if you were to compare ADAM against adaptive, momentum is the difference. Okay. Okay. Yeah, and I've just put this in different words. Second order moments, gradient squares help when you're already availing the first order moments. That's one aspect. Another important aspect here is adaptive is basically exploiting the quasi-Newton idea through the Hessians, or rather a low rank approximation to the Hessian. But in practice, it's actually very simple, right? All we talk about Hessians, etc., but in practice, all you're doing is multiplying the RHS by some alpha divided by square root of the ith component of the diagonal. So it appears to be deceptively very simple, the adaptive update, though it is actually inspired by quasi-Newton. Okay, then there is also some interesting paper. I don't know if anyone has picked this up for a seminar reading. There's a work by Wilson which says the marginal value of it talks about the marginal value of adaptive gradient methods in machine learning. So it says that, well, with all the advantages, adaptive is helpful, but it's not the big game changer here. It's good for theory. Momentum is actually the big game changer. Right. So that's a point here. Adaptive gradient methods tend to minimize training losses better. In practice, they do so by obtaining more complex and less generalizable solutions. So that's where the generalization capability becomes a problem, because they're reading too much into the curvature information of the function. Okay. Okay. So this is from the paper, and again let me highlight again. So what you have on the y-axis is a test error, and this is a test data. Okay. This is a training error. This is a test error. So you can clearly see that a method such as heavy ball is doing well on train and test, whereas the adaptive methods, I mean, they're not great even on train data here, as you can see, but the gap is only increasing on test. That is a concern. The gap becomes wider in the test data. Okay, if the ADAM in pink, right, versus AdaGrad, okay, you can see that the gap is actually widened in the test data. So the problem is even more pronounced on test data with the adaptive methods. Is there some other papers you could read, but we are going to move on to the next topic. Maybe 5 minutes. I just want to get started with the next topic. Okay, this I just gave us additional reading, which kind of helps you understand from a statistical pack learning perspective what these stochastic methods do. But this is all really extra reading. The key point here is the connection between pack learning, approximately correct learning, and vanishing of the regret. That's the point, right? So some of you kind of guess, right? If the regret would basically correspond to the loss if I had a stochastic sample, as against the loss if I had access to all the data. Right? So that there's a connection between the two. I just put it in the slides. So I just want to get started on this series of topics next, which gets us more into constraint optimization, and the idea of generalized gradient descent, of which proximal gradient descent, projected gradient descent, all of these are special cases. Okay, so let's understand this a little carefully. So far, okay, by the way, we are going back to excess variables. So we had used W as variables when we dealt with stochastic algorithms. So we'll use X now. Now, if you recall, in constraint minimization, when you have, let's say, a positivity constraint, you might not get the optimal solution simply by removing the constraint, right? Because if you remove the constraint, the solution might lie outside your feasible set, right? So in this case, for example, I might say, this is my constraint set. Let's say this green part, right? Now, if I optimize this function in this green space, obviously, this might be my solution. But my unconstrained minimum will be somewhere here, right? So how do I put in the constraint? How do I put in a constraint which could be also viewed as a function, but a non-differentiable function. Right? It's not even a continuous function. Okay. So we'll consider this very general optimization framework. Where we have F decoupled from C. So the C is going to be our set of constraints. Constraint based function. Okay, and F will have all the nice properties we have basked in so far, right? Which gave us all the convergence properties, the best of convergence properties. What we'll do is we'll say, well, is there a way we can separate the two? C could be constraint based functions. C could also be some of our uncomfortable functions, like the one norm. Functions for which we motivated subgradients. Do we need to combine them with F? Is there a way I can do a gradient descent on F and deal with the C separately? Okay. So F is amenable so say gradients, gradient computation. F could be smooth. Perhaps smooth and strongly convex, both. Okay, so is there something we can do? Any thoughts? Your seminar paper should also be read like this, right? You're given a problem like this. What would be, I kept asking this, what's a baseline? What would be a baseline approach? A baseline approach would be compute the subgradient for the entire thing, right? Let's say the whole thing is convex. Compute subgradient. So that's a baseline. We already said that. But now I want to do something more intelligent. What could you do? Separately optimize. Let's say I actually find a minimum. Let's say F is even amenable to a closed form solution. Then how do I handle C? Okay. But C may not be constraint based. C could also be a one norm. I want a more generic solution. So let's say C is one norm. What would you do? Okay, his suggestion is find a solution for F and then move around a bit and see if solution for C exists in that space. Okay, anything else? So good ideas. Yeah, we also use H instead of C at times to denote. So H won't denote constraints. C somehow keeps reminding of constraints, right? But no, one norm is easier indicated through some H function rather than C. I just made a note there. Okay, so just to give you a perspective, yeah. So the fx is let's say solvable using gradient descent, and one of the ideas was solve x directly, right? What I'm proposing here is slightly different. I'm saying, well, can we now view x as a solution, even xt plus 1, as a solution to a second order approximation, right? As some of you pointed out, it could also be the optimal minimizer of the function f. But for the time being, let's say that xt plus 1 is viewed as argmin over x of f of xt plus the dot product of gradient at xt with x minus xt and 1 minus gamma x minus xt square, right? So this is what gives you the gradient descent solution. Now, can this view, a slightly different view of gradient descent solution, give me a better answer? Because the answers so far were very hand wavy, right? Find an optimal solution, search around it. But I'm trying to give you some hint. Is this question clear? Is there a way I could use the fact that the gradient descent solution for f is minimizing a quadratic function? Okay, so can this help? Can this view help? This is gradient descent. Okay. Gradient descent update. Yes, anyone? I won't let you go till you answer this question. Very simple idea. Okay, here's an idea. Just add cx to this quadratic approximation. Just add cx to that. Why would that be helpful?
Just CF the value.
So I think the proposal is as follows. So let's give it a name. Okay. So let's call this QHT. Okay. So the proposal is proposal to ponder. Okay. So can I have an xt plus 1 tilde as the argmin over xt over x? Okay, by the way, qx is wrong to just call it qxt. Let's call it qx subscript t. Okay. So the proposal is xt plus 1 tilde be obtained as a minimizer of the quadratic approximation around x, around xt, right? Which gave you the gradient descent update plus cx. What is good about this? We don't have to attempt to find a subgradient for c of x. Why? They may still be interested in a subgradient. Okay, so I will show that in some cases. Okay, imagine I add a one norm here, right? Cx, the classic, I think the best example is if this is taken to be the one norm. A quadratic function plus one norm. What would happen? could I actually compute a subgradient for this function and actually find an optimal solution to this subproblem? I'm not saying the original subproblem. Okay, think about it. We'll continue this next time. You remember I talked about the lasso problem? We can find an optimal solution to the subproblem. Okay, so think about it. Okay, I'll leave it with this hint. So we'll have who's presenting? Who's presenting?